Welcome back to the another finite element analysis session. My name is P.NAVIN JASS, Assistant Professor, Department of Mechanical Engineering, Rohini College of Engineering and Technology. Today we are going to see the fifth unit of this course. The topic of this fifth unit is Isoparametric Formulation. Isoparametric Formulation. Here, this is the syllabus of the Isoparametric Formulation. Here we are going to discuss about the natural coordinate systems, isoparametric elements, shape function for isoparametric elements, 1 and 2 dimensions, serendipity elements, then numerical integration and application to plane stress problems, matrix solution techniques, solution techniques to the dynamic problems, and the introduction to the software analysis. Then this is a course outcome of this course. By the end of this course, we can able to explain the concept of using finite element methods to solve the isoparametric elements. Okay, this is the introduction for the isoparametric formulation or isoparametric element. In the finite element method, it is one of the powerful technique for analyzing the engineering problems involving complex and irregular geometries. The two-dimensional and three-dimensional elements like a triangle, rectangle, brick, these are things already we discussed in the previous chapters or previous problems or previous units, or cannot be used. These things cannot be used efficiently for irregular geometry. Okay, this is a figure shows the continuum with the irregular shape. It has not a definite shape, but it is in some like a oval, or it's not a proper manner. Here, in one diagram is in a normal continuum, and in another diagram it is discretized by the triangular elements. What is meant by discretization? Already we discussed in all the units or all the courses. We discussed about the discretized. It is nothing but it is the art of subdividing a structure into smaller number of convenient elements is known as discretization. So this continuum is subdividing a smaller number of triangular elements for the better analyzation. Okay, the next one is natural coordinates. It is used to define any point inside the element by a set of dimensionless numbers whose magnitude never exceeds unity. This system is very useful in assembling of stiffness matrices. So this system is very much useful in the assembling of stiffness matrices. So first we consider a line with nodes and natural coordinates and Cartesian coordinates. Natural coordinates and Cartesian coordinates. So here, this line element with two nodes with Cartesian coordinates x1 and x2, and that's a point P with Cartesian coordinates as well as natural coordinates. So natural coordinates are nothing but L1 and L2. Cartesian coordinates is x. So here, that's the total weightage of natural coordinates at any point is L1 plus L2, which is equal to 1, which is a unit. Okay, so this so we consider this as a first equation, and now the second equation as L1 into x1 plus L2 into x2. So we consider this as a second equation. We are rearranging the equations and as in a matrix form. Arrange the equations in a matrix form. So matrix of 1 1 x1 x2 into vector matrix of L1 L2, which is equal to vector matrix of 1 and x. So L1 L2 is equal to. So how we get this matrix? So how we get this matrix means now we are multiply and get the above two equations. So L1 row into column. So L1 plus L2, which is equal to 1. This is the first equation. L1 plus L2, which is equal to 1. Now the second equation, L1 into x1 plus L2 into x2 is equal to x is the second equation. So by this we arrange these equations in a matrix form. Now we are going to transfer this matrix from left side to right side. So L1, L2, vector of L1, L2 is equal to matrix of 1, 1, x1, x2 inverse into vector of 1x. Now, which is equal to, now we are dividing the equations with x2 minus x1, x2 minus x1. So 1 by x2 minus x1, the equation changed into x2, matrix of x2 minus 1 minus x1, 1 into vector of 1x. Vector of 1x. So this inverse is gone. Now this method comes under the formula of this formula. Okay. Now then, which is equal to 1 by x2 minus x1 vector of x2 minus x minus x plus 1. So which is equal to 1 by x2 minus x1 vector of x2 minus x minus x1. So which is equal to 1 by L into x2 minus x minus 1 x1. Therefore x2 minus x1 is the length of the element, which is called as L. So L1 L2 is equal to x2 minus x by L and x minus x1 by L. So variation of L1 and L2, as we saw in the diagrams, the first diagram shows a one-dimensional line element. The second dimensional, which is a variation from the line element, variation of L1 and variation of L2. L1 is 1 at node 1. Variation of L1 is nothing but at node 1 it increases to 1. Variation of L2 is nothing but at node 2 it increases 1. Okay, so therefore integral of x1 to x2 L1 power alpha L2 power beta into dx is equal to alpha factorial into beta factorial divided by alpha plus beta plus 1 the whole factorial into Lx. Alpha factorial is the factorial of alpha. Now natural coordinates in 2 dimensions. Now we are considering a triangular element having 3 nodes as shown in the figure. Consider a triangular element having 3 nodes that we saw in the figure. P is the point inside the element. This is the figure. We are considering a triangular element having 3 nodes as shown in the figure. What are the 3 nodes? 1, 2 and 3. These are 3 nodes as shown in the diagram. We are considering the triangular element. Now let P is the point inside the element and it has 3 coordinates L1, L2 and L3. Okay, here there are 3 coordinates at point P, L1, L2 and L3. From the definition of natural coordinates, we know that L1 plus L2 plus L3 is equal to 1. So L1 into x1 plus L2 into x2 plus L3 into x3 is equal to x, and L1 into y1 plus L2 into y2 plus L3 into y3 is equal to y. So now we are assembling these equations in a matrix form. So matrix of 1, 1, 1, x1, x2, x3, y1, y2, y3 into vector matrix of L1, L2, L3 is equal to vector matrix of 1, x and y. Now we are transfer this from left side to right side. So L1, L2, L3 is equal to integral matrix of 1, 1, 1, x1, x2, x3, y1, y2, y3, the power inverse into vector of 1, x, y. Now we are taking this matrix as D. So D is equal to 1, 1, 1 minus x1, x2, x3, y1, y2, y3. So D inverse is equal to C power T by D determinant. So what are the coefficients of matrix D? So C11. So now we are considering this as a C11. For C11, the coordinates are x2 minus y3, x2 into y3 minus x3 into y2. x2 into y3 minus x3 into y2. Likewise for C12, minus is here the minus symbol. So x1, x3, y1, y3 determinant is equal to minus of x1, y3 minus x3, y1, which is equal to x3, y1 minus x1, y3. Likewise for C13, x1 into y2 minus x2 into y1. C21 minus of y3 minus y2, which is called as y2 minus y3. Likewise for C22, y3 minus y1. C23 minus of y2 minus y1, which is equal to y1 minus y2. For C31, x3 minus x2. C32, x1 minus x3, and C33, x2 minus x1. Now we are substitute these equations in the matrix. So C is equal to x2 minus y3 into x3 y2, x2 y3 minus x3 y2, x3 y1 minus x1 y3, x1 y2 minus x2 y1, y2 minus y3, y3 minus y1, y1 minus y2, x3 minus x2, x1 minus x3, x2 minus x1. Now C power t, C transpose is equal to x2 y3 minus x3 y2, y2 minus y3, x3 minus x2. Here the rows are changed into columns and columns are changed into rows. Now D is equal to matrix of 1 1 1 x2 x1 x2 x3 y1 y2 y3. Now the determinant of D is equal to 1 into x2 minus x2 y3 minus x3 y2 minus 1 into x1 y3 minus x3 y1 plus 1 into x1 y2 minus x2 y1. Now we are substituting the C power t and D determinants values in the D inverse equation. So we get the value as D determinant D inverse is equal to 1 by x2 y3 minus x3 y2 minus x1 y3 minus x3 y1 plus x1 y2 minus x2 minus y1 into matrix of x2 y3 minus x3 y2, y2 minus y3, x3 minus x2. So x3 into y1 minus x1 y3, y3 minus y1 into x1 minus x3, x1 y2 minus x2 y1, y1 minus y2, x2 minus x1. Substitute this D inverse value in the equations. So L1 minus L1, L2, L3, which is equal to 1 1 1 x1 x2 x3 y1 y2 y3 inverse into vector matrix of 1 x and y. Now again L1, L2, L3, which is equal to the equations 1 by x2 y3 minus x3 y2 minus x1 y3 minus x3 y1 plus x1 y2 minus x2 y1 into x2 y3 minus x3 y2, y2 minus y3, x3 minus x2, x3 minus x3 y1 minus x1 y3, y3 minus y1, x1 minus x3, x1 y2 minus x2 y1, y1 minus y2, x2 minus x1 into vector matrix of 1 x and y. Now we are going to find out the area value. How we are going to find out the area value? Area is equal to 1 by 2 into determinant of 1 x1 y1, 1 x2 y2 and 1 x3 y3. By this 1 by 2 into 1 into x2 minus x2 y3 minus y2 minus y3 x3 minus x1 into y3 minus y2 plus y1 into x3 minus x2. So finally the area value is equal to 1 by 2 into x2 y3 minus x3 minus x3 y2 minus x1 y3 minus x3 y1 plus x1 y2 minus x2 y1. So the final value is x2 y3 minus x3 y2 minus x1 y3 minus x3 y1 plus x1 y2 minus x2 y1, which is equal to 2a. Therefore, L1, L2, L3 is equal to 1 by 2a into x2 y3 minus x3 y2, y2 minus y3, x3 minus x2, x3 y1 minus x1 y3, y3 minus y1, x1 minus x3, x1 y2 minus x2 y1, y1 minus y2 and x2 minus x1 into vector of 1 x and y. So therefore, the integration of polynomial terms in natural coordinates for two-dimensional element can be performed by using the formula integral a of L1 alpha, L2 beta, L3 gamma, dA is equal to alpha factorial, beta factorial, gamma factorial divided by alpha plus beta plus gamma plus 2 the whole factorial into 2a. So the next one is isoparametric element. So generally it is very difficult to represent the curved boundaries by straight edge elements. A large number of elements may be used to obtain reasonable resemblance between original body and the assemblage. Here, from the diagram, we can able to know these dots are called as nodes used for defining geometry. These dots are nodes used for defining geometry, and the triangular structure are called as defining displacements. So dots are called as geometry and triangles are called as displacements. If the number of nodes used for defining the geometry is same as the number of nodes used for defining the displacement, then it is called as an isoparametric element. Here in the diagram, in the XY diagram, there's an irregular structure, and in this irregular structure there are number of dots which we define, which is defined as geometry, and number of triangles which is defined as displacements. Okay, now we are going to check how many number of displacements and how many number of geometries. Okay, now we are going to check the how many number of geometries are there. So 1, 2, 3, 4, 5, 6, 7, 8. So 8 geometries are there. And how many displacements are there? So 1, 2, 3, 4, 5, 6, 7, 8. So that is also 8. So there are 8 number of dot elements which is defining the geometry, and 8 number of triangular elements which is defining the displacements. So if the geometry nodes and the displacement nodes which are equal, then it is called as an isoparametric element. Superparametric element. What is a superparametric element? Here, now we are going to check how many number of nodes are there for defining geometry are there, how many numbers of displacements are there. So first we are going to check the geometry. So 1, 2, 3, 4, 5, 6, 7, 8. 8 nodes which are defining the geometry, and how many nodes which are defining the displacements? 1, 2, 3, 4. Just 4 nodes. So here geometry, the nodes which are defining geometry is greater than the displacements. So if the nodes used for defining the geometry is more than the number of nodes defining the displacements, then it is called an superparametric element. Then it is called a superparametric element. Then what is a subparametric element? Here the number of nodes defining geometry and number of nodes defining displacements in the diagram. So now we are going to check how many number of nodes which are defining the geometry. So here 1, 2, 3, 4. Just 4 nodes are defining the geometry. Then how many nodes which are defining the displacements? Okay, here 1, 2, 3, 4, 5, 6, 7, 8. 8 number of nodes which are defining the displacement. So here number of nodes which are defining the geometry is less than the number of nodes which are defining the displacements, then it is called an subparametric element. Subparametric element. So by this session is over. Next topic we are going to discuss in the next session. Thank you.